Yeah, no one's here. I was wondering if I went to the wrong place.
Isn't it supposed to be? Oh, he did say there's another lecturer, right?
Me?
Yeah. Sorry, I didn't turn around. Were you sitting in class yesterday?
Yeah, there.
Oh, so I didn't turn around and see you, but I heard. I remember.
Yeah.
Getting another lecturer.
You're coming to the right place.
Yes. This is hydraulics, isn't it?
Yeah.
Oh God. It's raining cats and dogs out.
Maybe that's why nobody's showing up.
Probably that and the traffic.
Traffic's
Rainy
bad.
days, that's when everyone decides to drive.
Traffic bad.
Hmm?
Traffic bad.
Yeah, very, very bad. Meanwhile, what's up? You take hydraulics? Yes, I take hydraulics.
Hello.
Good morning, how are you?
Good.
How's your holiday been? Working up north. Busy. I'm tired. I did not give myself a break. I should have. Oh no, but that's alright. Working also means earning money. Yes, money. You're on holiday. Your answer is very business. I'm very underskilled, so I'm just trying to upskill myself slowly. Oh, don't even worry about it. I'm still like doing damage mapping and stuff again. It's all that basic stuff, and then they'll build this up. But I don't even know how to use it. I'm still like trying to get it working. If you need help, I'll try and help. Oh, thank you. I'm very like, I only started halfway through last semester, so. Hey, you learned it during semester. That's impressive. Hey, you learned it during semester. That's impressive. It's good to like have during semester because you can study at your desk. They let you just sit there. I try to work out the perfect time. Yes, we met. Yes. Yeah, that's done in 1 minute. Yes. Yeah. Lovely. Thank you. Is it new? Yeah. What was you saying? Like 34, only 34% of students pass the final test. I did not read that stat. I was just like, oh, maybe I should have. I thought you were the only one. No way. I didn't think so. It wasn't me. It's very good for me that you do it. Doesn't matter. Like HT's a HT boy. I'm just glad I didn't get it.
Hello everyone. Shall we get started? Not too many students, probably due to the weather. But yeah, I think they will watch the video anyway. So this is our first module. It's based on the equations of motion applied to a control volume. So as the other professor talked about yesterday, we have three major equations, the 0.2, 3, and 4. So the first is that we need to find a control volume. Control volume is sort of like a free body diagram as you do in solid mechanics. So the difference is that we are dealing with fluid. So the fluid is moving, but we normally choose a control volume that is fixed, although the fluid is coming and going, but the control volume is fixed. So it's sort of like a solid body. So we can choose it and do the fluid type of free body diagram so that we can solve for the forces and the flux. And then another thing is how we define a control volume, how we choose it. We can choose a fixed one or moving one or anything. We can talk about it later. Then the three major equations, one is conservation of, let me see the pointer, the mass. I can't do it on the screen because of the students who are watching the video. So second is momentum, then the energy. So these are the three major equations which is related to the fluid mechanics because of the conservation mass and the forces, force balance, and the energy coming and going. And if there's no supply and dissipation, then the energy is balanced. The key concepts, the first is the control volume we talked about. It's similar to a free body diagram. we select a region in space, and it can be chosen in any way. It does not have to be fixed, does not have to be moving, but sometimes there are certain ways we can choose it to benefit our calculation. For example, if we estimate a bubble that is moving upward in the fluid, then we might choose a control volume which is fixed to the bubble instead of the Cartesian coordinates. But if it's a fixed body like a pipe, the pipe is not moving, but fluid is coming and going, then we might choose a fixed control volume. The next thing is about the flux of mass. Flux is a time derivative of something. So here it's time derivative of mass. So in hydraulics, we normally use volume flow rate to represent the flux of mass because it is most straightforward to use a flow rate in fluid mechanics because the fluid is flowing and it's easier to consider its volume, its flow rate, rather than the mass itself. The flow rate has a unit of cubic meter per second. And so it's like when we talked about the flow rate of a river, it can be 1,000 cubic meters per second, or from the tap, it can be 0.1 cubic meters per second. Then about the flux of mass. Flux of mass is the time derivative of mass, partial t. So here this is mass. So it's m on t. My right is here. The mass is rho times v, the uppercase v. So it's straightforward. And here, the volume is the flow rate times t. So if we do not consider t from here and here, then it's rho times q. So that's mass flux. Then finally, if we know the mean velocity, here it is the mean velocity rather than velocity at a certain point because we deal with relatively large scale structures like the pipe and open channel, river, or atmosphere. So it is a relatively large body rather than the molecular scale. So we normally use the mean velocity to represent the flow. So it's easier, although the distribution might not be uniform. But in terms of the large scales, we can simplify the problem. Then the flow rate is Q equals U times A. So a few examples. For example, a pipe. If there's a pipe, a circular pipe, and we look at the cross-section, that's the area. And we have a mean velocity. Although the distribution might look like this because the boundary, the velocity will go to 0. We do not need to memorize all this here, but in the future, we will encounter these problems. Here it's just a demonstration. Then the flow rate would be U times A. So for example, if we have a flow rate 1 cubic meter per second, then if you stay at the end of the pipe, you can collect a cubic meter per second. So every second you can collect a cubic meter of water. So that's the flow rate. Also, like the open channel, if we have a channel, and here is the free surface, the difference between the pipe and the free channel, open channel. So that's the velocity, mean velocity, and area, the dashed area. Then we have the flow rate, U times A. U is the mean velocity. This can be extended to a natural river where the shape is not so rectangular. Next, it's about how we choose a control volume. There are a lot of ways, like the first one, although the system, the solid lines is fixed, but the control volume can be part of the system. Or in most of the conditions, it is right from the inlet to the outlet. And it can also be a different shape, or as I talked about before, it can be moving with a bubble or something. And we will, for each problem, we will see how we can choose the control volume. And in most of the cases, this is the case. So let's come to the first major equation, the conservation of mass. So here we have two equations. The first one, you see there's a sigma. It's like there are, this pen's not very good. Find another one. So we have a random control volume, the one here, it's a control volume. So if we assume there are a few inlets and outlets, so for example, this is in, this is out, a few, a finite number of inlets and outlets, we can use sigma to add them together, like the or the in or the out would be these two terms. But if there are a lot of, or if the this is a general condition. So if there are a lot of inlet outlet, and in a more elegant way, we can do integration. So this is the integration form. This is the integration form of the conservation of mass. So there are two different expressions. So for the first one, we can write it in a simpler way. The mass in the C control volume equals to the mass in minus mass out, also plus mass originally within the control volume. So this is a more understandable way. So amount of the mass, then how much comes in, how much comes out. Then it's like when you are, it's like a bus full of people. If there are 3 going onto the bus, then 3 have to go out, right? So it's like a conservation of mass. And then normally in fluid mechanics, we deal with the flux of mass. That's the time derivative. So we use partial t for each and every term. Then we come to this equation. So m dot is partial t. Then we have the equation. Simply use a dot, but it's equivalent to the partial t. And the original one, if we do the time derivative, that will go to 0. So that's how the first equation comes. Then the second form, the integration form, it's a little bit more complex, but it's basically the same. If we do an integration of dm dt, then in terms of the volume change, so the change of the volume in the control volume, so without inlet outlet, that's m is rho times v. The uppercase V is the volume dt. So if we take rho out, then this is the left-hand side of the second equation. Then in terms of the area, if there is fluid mass coming into the control volume or if it goes out, if we only consider the fluid goes out, then if that's coming in, that we just use a negative sign. So the second term is derived based on still rho v, the volume, dt, but here the volume is based on, so if we assume this is control volume, there's a pipe or anything, a jet, then we have an area. This is the dA, like expressed in, can't find my point, in here. This is a small area dA where the fluid is going out. So it's very small, it's dA here. And velocity is actually perpendicular to the area, so we can calculate the velocity and times the area. So dA, u dA is the q times t, then we have a volume. So we have this amount of volume going out. We replace v as u times t, then dt, which gives us rho u and a. So that's the rho u dA here. So we assume rho and u are not related to the integration, a constant. Then we have the second expression. And then for engineering practice, we can simplify the problem. First simplification is the flow is steady. So that means there is no accumulation of the mass in the control volume. So how much goes in, and then the amount will go out. So the first term is 0. And this gives us mass flux in equals mass flux out. So the two terms on the right-hand side, then one goes to the left, then so in equals out. And a second, then we assume the flow is also incompressible. Incompressible, I can explain it a little bit. So incompressible means the speed of the fluid, no matter the type of the fluid, the speed is less than 0.3 times the Mach number. So the velocity is less than 0.3 times the speed of sound. It's around, so if the velocity is smaller than 100 meters per second, we assume the flow is incompressible. So the compressibility is affecting the fluid by less than 5%. We can assume it is negligible. So whenever the velocity is less than that, in most of the cases in our unit, the flow is incompressible. So normally we deal with air and water. And for strong wind, like the wind today, the velocity is around 10 meters per second. For a super strong typhoon or something, it can up to 60 meters per second, but it can hardly exceed 100 meters per second. So normally in air, when we deal with like the pollution in the city, and we consider incompressible fluid as well. And also for water, if it's strong, a very large dam with spillways, for the flood season, the spillway will open, and then the discharge velocity is around 35 meters per second. So it's also incompressible in most of the cases in civil and environmental engineering. So here we assume it is incompressible, which is valid for most of the cases in civil engineering. Then because m dot is rho times q, then the rho for the two sides can be canceled out because the fluid density does not change. Then we have the equation based on the second simplification. So this equation is based on both of the simplifications, just one step, another step. So we have the volume flow rate in and out would be the same. And for the last step, if we define the mean velocity and Q can be expressed as the velocity times the cross-sectional area the velocity goes through. Then we have the final expression. I can write it here, but you can add it to the end of the slide. That's the velocity and area in and out would be the same. And we have a sigma here, so if there are several pipes discharging water, we just combine them to the right-hand side. So we have a very simple example. It's like a pipe, but there's a contraction. So the cross-section area for the left-hand side, let's denote it as 1. And the right-hand side is 2, would be different. So we can assume the velocity will also be different. Then we can calculate the velocity for the two sides. We can calculate actually both U1 and U2. So although here it asks for U2, but we can also calculate U1. We have been given a flow rate. So flow rate is not changed. And so we can safely assume it is also steady flow because the flow rate does not change. There's no accumulation within this amount within the pipe. And we are given the diameter of the two sides. Then we can use this equation to calculate the velocity because we know the volume flow rate, we know the diameter of the pipe or the area of the pipe where the fluid goes through, then we can calculate the velocity. So we can assume the flow is steady and incompressible. So based on the previous slide, we can use the simple form of the equation, Q in equals Q out. And here, because there is only one inlet and only one outlet, we can define inlet as 1 and outlet as 2. Then for the Q in, it equals to U1 and A1 for the location 1. U1 is what we are going to solve, and A1 is pi d1 squared over 4. And the flow rate is given 0.3. So this gives us U1. You can double check the calculation later. I'll give the answer directly. So that we can do the same for the location 2. And we also have the same flow rate. We can work out the velocity for the second point. Is it a bit small or is it fine? It's fine, okay. So we can see, double check, the velocity, highest velocity is around 38, so it's well below 100. So our assumption is correct, so it's incompressible. And here, because of the contraction, we have a much increased velocity for the outlet point. Let's moving on to the conservation of momentum. So this one, this will be uploaded to the LMS, and you can see the solution later, or you can even take a photo after the lecture. So conservation of momentum. Momentum is like a force, the force induced by the fluid. And it's basically the Newton's second law of motion. It's similar to solid mechanics. When you push a small car, then it moves. So we have the force equals to the mass times the acceleration. So it's in vector form. If we push the car in this direction, then we'll accelerate in that direction as well. And here, we want to, we can replace acceleration as the, so this is velocity actually. This is the lowercase v. So the uppercase is normally representing the volume. So here it's the velocity. And here, mv is called a linear momentum, or momentum for short. And we can state, based on the Newton's second law of motion, I can find my point, the rate of change of the momentum of a body. So within a body, if the momentum changes, then it is equal to the net force acting on the body. So if there's several forces acting on it, it will cause the change of a momentum within the body. And we apply this equation to the control volume to determine the forces. So the equals to the net force. We calculate the change of momentum of body, then that must be due to the force acting on the body. The forces, there are some forces, including the body force and surface force. We will talk about those in next slide. Then the conservation of linear momentum is expressed as the sum of all external forces acting on the control volume. The first term is corresponding to the forces here. Then the change within the volume is the change of the momentum. And here, the change can be separated into two terms. The first term is the change within the control volume of the contents of the control volume. It's within the control volume. So it's either absorbed by the control volume, or if cannot, or if it does not want to, it can also go out of the control volume. So it's like across the boundaries of the control volume, it goes out. So the work done, the forces acting on the control volume, it can either take it or it can spread out of the control volume. So there are two terms on the right-hand side. And for the mathematical expression, we have the rate of momentum accumulation within the control volume. This is for the left-hand side of the previous slide. No, sorry. This is our right-hand side. This is the force, the left-hand side. This is the first term on the right-hand side and the second term on the right-hand side. We can explain these two terms. So the first term on the right-hand side, the first term shown in the slide, is in terms of the volume. So it is accumulating within the volume. We have dm dt. So here you see the dm dt. But we take into account the velocity later. So this is for the expression of rho dv over dt. So this is an expression for the conservation mass, as you can recall from the first equation. Then if we also consider the velocity, it can be either expressed as u or v, but it's a vector form. dt, just to add another u here, we have the integration based on the volume, rho du, rho u dv, rho v is the mass. So this is the first term on the right-hand side. So it accounts for the increase of the momentum in the control volume. It's not going out of it. And second, in terms of the area or the boundary of the control volume, it spreads out. For the conservation of mass, we have the integration around the boundary of the control volume. So UN is the velocity perpendicular to the boundary of the control volume. As for the momentum, we just add a vector velocity in terms of integration based on the area or the boundary. That's why we have one vector form of the velocity and the other is perpendicular to the boundary of the control volume. Here, two velocity components. And then we have the integration form of the conservation of momentum. Then in a general case, if we look at a finite number of pipes going in and out, then we can use the sigma to add a few pipes, a few inlet and outlet. And this is the same expression as the previous one, all the forces, and it's just we separate inlet and outlet for ease of calculation. And then if we assume the flow is steady, the steady and incompressible will be used for all three equations used in this unit. And if it's steady, so the partial t term will go to 0. And we have the two terms on the right-hand side equals to the force, total force. And a few notes. The first is that this equation, 1.6, or the steady form, is a vector equation. As you can see, the force has a direction, as well as the velocity has a direction. So the velocity, if the velocity or if a water jet is pointing at me, then it will acting on me with a force, pushing me backward. So whatever the direction of velocity is, the force will be in that direction as well. And then, also for each direction, it's like the, yeah, we will talk about that later. And second note, if there is a change in momentum flux in one direction, then the force is acting in that direction. So it's basically similar to the first note. Note 3, common forces, including the gravitational. Gravitational is the body force. Fluid pressure, viscous, surface tension. So these are all on the surface. The pressure is like, if we have a pipe, the left-hand side, if we just cut the pipe in half, then the fluid will collapse, right? But because it is connected by the two sections of the pipe, then the pressure balances out. That's why the fluid is within the pipe and it's not flowing out. So there is pressure in the pipe flow. And the viscous or shear force, if the fluid is moving on the ground, then we talked about the boundary layer yesterday. The velocity on the ground would be 0, and the velocity far above would be the free stream velocity. Then it will reduce in a log profile. That's due to the viscous force. Then surface tension, it is related to a very small object, like the insects sitting on water or small animals running on water. It's due to the surface tension to balance out its weight. So surface tension is normally for very small objects. It's not related to large objects like the ships. The surface tension would almost be negligible. And the last is force due to solid objects in the CV. And this is normally the force we solve, like if you there's a plate and a water jet impacting on the plate, then how much force do we need to hold this plate in to hold it still? So this is the force impacting on the plate, which will balance out the momentum force from the jet, and it will balance out the forces for the control volume. So that's the force due to a solid object like the plate. And we do not have to consider all the forces. For specific problems, we consider some of the forces. For simple problems, maybe just one. For the plate one, we can just consider force due to the solid object. But for some complex problems, if you encounter in the tutorial, we may use a few, like 3 forces, and you just add all the forces and just pay attention to the direction, because the force is a vector form of the force. So just consider all the forces in that direction. Here also on forces acting on CV. So as we talked about, there are body force and surface force. The body force, normally we look at the gravitational force. The body force means it's acting on each and every point within the control volume. So the gravity is, of course, acting on all the objects, no matter large or small, on Earth. And there are also magnetic force, but we do not consider those in this unit. So the only body force is gravitational. And surface force, all the rest. And the reaction force is like the force acting on a solid object. It will have a reaction force on the control volume as well. And next, pressure force is always perpendicular to the surface of control volume. So pressure force is pressure times area. So the pressure is always perpendicular to the area it acts on. And that's why the pressure force is perpendicular to the surface of the control volume. Then how do we determine the pressure in a fluid? Because pressure is a very common variable we encounter in fluid mechanics. For like hydrostatics, and for A and B, we will also revisit them in Module 6 in hydrostatics. For hydrostatics, for example, if there's a dam, and here's the free surface, and then the pressure at a point underneath the free surface, we have a pressure. The pressure can be simply calculated as rho g times h. The h is the height from the free surface to this point. So similarly, when in a pipe, we want to predict the pressure at the pipe. So if we want to look at the pressure at this point, the red point, this is the free surface. We can use some device called piezometer to calculate the pressure. So this is the free surface in analog to the free surface here. And this is a point we want to estimate. Then if it gives a reading of h from the top of the, from any reference point to the free surface, then we can work out the pressure of within the pipe. So h is P over rho g. So the 2 examples are basically using the same equation. As for a free jet, it's different from a pipe flow because the pipe, it's compressed. The pressure is driven the fluid moving to the other side. But for a free jet, it is surrounded by atmospheric pressure. The atmospheric pressure, we can assume it is 0 for a reference, but it has an absolute value because we are all surrounded by it. We can use it as a reference, so we don't have to consider the pressure inside or outside the body because we are all surrounded by atmospheric pressure. So if we assume this is 0, then the pressure of the water jet is 0 as well, because on the On the outside of the water jet, it is connected to atmosphere, then it's definitely 0. And inside it, and because it's a free fall, then it's not actually supported by water particles around it, then the pressure would be the same as the edge of the water jet. So we have the atmospheric pressure for the free jet. Then we recall the two expressions of the equations for the conservation momentum. The first, similar to the conservation of mass, the first is the integration form. The second is the just to add all the components, all the inlet, outlet. So it's more straightforward for our daily use in engineering. Then for the second form, if we expand it to the three directions, the x, y, and z, if we use the right-hand rule for x and y, z, so as you can see, x is to the right, z is to top, and y is going inside of the paper. It's not going outside because we follow the right-hand rule for all the problems in fluid mechanics. Right-hand rule can be expressed as if the four fingers goes from x to y, then z is the pointed by the thumb, so x to y, then that goes up. Or if we another way, this is x and this is y, so the first three fingers, then the z is pointed by this finger. So they are basically the same. It just tells you how the three coordinates are linked together. So if we expand the equation to the three directions, then we have the three terms, fx, fy, fz. And for some problems, we do not have to consider all of them, because if we want to calculate the horizontal force, we can just take the first equation and apply it for the fluid velocity in the x direction. And in most of the cases, because we consider steady flow in our unit, then the first term, the partial t, will go to 0, and it is simplified as the addition of out minus is or the in. And then we can apply these equations for most of the problems encountered in this unit. So here we have an example. Water is accelerated by a nozzle. We can draw a sketch. Water is accelerated by a nozzle so the nozzle will go from here, but we don't have to consider it, to average speed. As you can see, this is the mean velocity of 20 meters per second. Then strikes a stationary vertical plate, the one with a shaded shape, at a rate of, this is flow rate, liter per second. It's different from the conventional cubic meters per second. So if it's 10 liters per second, that means 10 divided by 1,000 cubic meters per second. So for the calculation, we first convert all the numbers to a standard unit set. So for liter, we pay special attention. We need to convert it into cubic meters per second. And also like the centimeters, we need to convert it to meter. And after striking, so this is the velocity at 20 meters per second. After striking, the water stream splatters off in all directions. All directions, goes up, goes down. So actually, this three-dimensional problem, the jet goes from left to right, and there's a huge plate, and it goes around it, so it's all directions, up and down, left and right. Then determine the force needed to prevent the plate from moving horizontally due to the water stream. So as you can see, it asks us to calculate the force to prevent the plate from moving horizontally. Horizontally means the x direction. So we need to apply a force to hold the plate because from intuition, if the velocity goes from left to right, it will have an impact force. Then we need to hold it. So the force will go opposite to the direction, although we will calculate it later, but we need to hold it with that force. So in this case, we can consider the x direction. So first, let's assume, so this is a solution. We can assume the flow is steady and incompressible. And then, so after this assumption, we can use the formula given in the previous slide. Then the second step, we need to choose a control volume. The control volume, it can be either it can either include the plate or it does not include plate. So in this case, we can use a control volume that is the dashed line here. So this is a control volume. The amount of the water here. So if we draw another sketch, this is a control volume, the water. Then we have an inlet velocity, 20 meters per second. So that's U in. And we have some outlet. So although it is drawn like two ways, but actually it goes around this plate. So there's some rho Q U out, or just say U out. Rho Q would be the force. Or we can also say this is rho Q U in. So if it's a force balance, like a free body diagram, then we need to have some force to hold this plate. We don't have to say this is to the left, but there's a force. We can work out the direction of the force later. So this is our control volume or free body diagram. Then in the horizontal direction, we can work out the force. So the basic formula is written in this way. So out is the first, then minus in. So that's the equation. Then, because there's only one force, the force due to the solid objects, there's only one force in horizontal direction. For vertical, we need to pay attention. There is a gravitational force everywhere, but in the horizontal direction, there's only one force due to the plate. Then, so this is actually the force from the plate to the control volume. We are looking at all the forces acting on the control volume. So this is the force acting on the control volume equals to, because all the outward directions are not in the horizontal direction, it's all in the y and z plane. So this is x, but the out is not in the x direction because as you can see, there's a plate to reduce the velocity to 0. At if you will say this is outlet, then the velocity will go to 0 in the x direction. So for the in, there is one inlet, only one inlet here. We know the velocity, we know the flow rate. Density, we can use 1000 or sometimes 998 for the solutions given in the tutorial, but you might notice a very small percentage difference in your calculation, like less than 1%, but it doesn't matter. Sometimes it is caused by the density. And this is the flow rate, 10 liters per second. It's converted to the cubic meters per second. Then we have the velocity u in. This gives us a negative force, so minus 200 newtons. So these are all the standard units. This gives us straightforward to the newtons. Then because we assume the positive x direction, as you can see, is to the right, so as the velocity of in. So here u in, it is positive, but there's a negative sign here, so the total force will be negative. And here it gives us negative force, which means the force acting on the control volume is opposite to the x direction. We assume then it is to the left, as the same as our intuition here. You out, right? This term, right? Okay, yeah. Because we look at the horizontal direction here. Yeah, so yeah, this is 0. No, there's no silly question. Welcome all the questions. That's the benefit of you guys waking up early and come to the class. So here, any questions, just raise your hand or just let me know. Here, the velocity out goes to 0. So actually, if we draw some streamlines, the velocity will go to all the directions parallel to the plane, right? It does not go through the plane, it goes around it. So that's why in the horizontal direction, it goes to 0, but in other directions, it might be of some value, like in the vertical direction. But just another note, because it goes around the plate, the forces will cancel out. It goes every direction, then the left will cancel right, up cancels down. There are some problems, 1, 2, 3. We can talk about this on Friday. So I'll see you on Friday then. Any questions can ask after class, or just take a photo of this, or look at the solution on the LMS. So I'll see you on Friday then. And there's no tutorial this week, so tutorial comes next week.
They're actually like a.
Specialist 1000. Yeah.
Yes. Yeah. So this is density of the water.
Oh, okay.
Yeah, we need to memorize the density of the water.
Which one? Oh, engineering Nick. Actually, oh, Nick, he don't. Oh, he's a nice bloke. When he need to do visualization and sorry, data analysis. Pathology stuff. Maybe not. Lecture room, 130? No, not medicine.
data collection and analysis. Is that the one?
In the right spot.
Okay.
What's up?
None of them. Good it was.
You knew you were taking this one. So you don't want to keep it.
Yeah.
Three. That's what I was thinking. You know, I shop before you